Physics 2211, Lab 5, Falling Slinky. The purpose of this lab is to compare the motion of a falling slinky in the real world to a computational model. Specifically, I want to determine if the bottom of the slinky in the computational model will move in the same way as the real-life experiment. For this investigation, I will be making use of Tracker to track the motion of the bottom of the slinky and GlowScript to create the computational model of the falling slinky. Preview of results. The bottom of the slinky moved roughly the same in both the experimental and computational models. We will be making use of Newton's second law, also known as the momentum principle. This law states that the change in momentum over time of a system is proportional to the net force acting on the system, where F net is equals to dp dt. Drag force, air resistance, is the resistive force acting on bodies as they move through fluids, e.g. air. This is one of the forces we'll also be making use of in this investigation, where F drag is equals to minus b v squared v hat, where Fd is the drag force, b is the proportionality constant, and v squared is the square of the velocity of the system, and v hat is the direction of the velocity. Here we'll be also making use of gravitational force. The gravitational force will be equal and opposite to the tension force action on the slinky, which will cause the bottom to not move when let go from rest. So you can see that Fg is equals to minus mg r hat, and Ft, the tension force that's acting on the slinky, is equals to minus Fg, which is equals to mg r hat. Observed motion. For the observed motion, I used a clip from the Veritasium video where a professor dropped a slinky at a height from rest. System is a slinky, surroundings is the earth, and people. Assuming it is an average slinky, the mass is 0.2 kg, and Veritasium's height, for reference and calibration, is 1.78 meters tall. Initial conditions. The velocity is 0 in the x hat, 0 in the y hat, 0 in the z hat meters per second, because it is initially at rest, and the initial position is minus 2.166 times 10 raised to power minus 3 in the x hat, minus 1.877 times 10 raised to power minus 2 in the y hat, and 0 in the z hat meters. And total time is 8.52 seconds. So here's the video of the experiment and the tracker that I used. Look at all the dots being placed and how it's falling, and the recorded data. So here is my model and GlowScript code. Here I put in the mass of the slinky, the initial position and velocity, and the proportionality constant that was found through trial and error. In the first while loop, which would calculate the position of the bottom of the slinky before it started moving, the force of gravity and the force of tension opposing it are equal and opposite, as shown with the equations. Another while loop is shown, which will calculate the net force acting on the slinky after the bottom part starts to move, using the gravitational force and the drag force, and will also calculate the change in position of the bottom of the slinky. So as you can see in the first while loop, the time was up until a certain time, which is when the slinky started to fall, and this is the time for the whole experiment for this second while loop. So here's the graph of the results. The experimental position is in blue and the model position is in red, the change in position over time. So as you can see, that the graphs look quite similar, and they're quite similar in shape. The model position is a little bit more straight, and the experimental position is a bit more all over the place, but they follow roughly the same trend. So errors and assumptions I made throughout this investigation. While the graphs look very similar, the observed motion experiences fluctuations due to other forces not accounted for in the model, therefore they don't line up completely. Moreover, some of the tracker points may not have been placed in the right place, which may have reduced accuracy. Also, while the actual time it took for the slinky to fall was less than 5 seconds, I assumed that it was the time 8.52 seconds shown previously, as to model the real-life motion of the slinky. I used a slowed down version of it falling for greater accuracy, which took 8.52 seconds. This is what caused the time period to be increased. However, the model still holds up despite this. It still shows an accurate representation of how the slinky is falling despite the time discrepancy. What if? What does it mean? Why does the bottom of the slinky remain stationary? Although the gravitational force acts downwards, the slinky counteracts this force with an equal and opposite tension force, meaning that the forces in the y direction acting on the slinky at the bottom cancels out. What if we put a weight on the bottom of the slinky? If the slinky is long enough and has a large enough spring constant to overcome the force of gravity, making them equal and opposite, then the bottom of the slinky could remain stationary when first dropped, even with the weight. Thank you.